You.
Okay, thank you very much. So I've been teaching a course on performance evaluation here at EPFL. It's not a big class, it's a small class. It has been given over the years with about the same attendance, about 25 to 30 students. It hasn't grown up, it hasn't declined either. But in the recent year, I was surprised by some feedback I received from students after the course, where they told me that, in fact, yeah, the course was interesting, queuing theory, all that stuff, sure. But the thing that they got from the course that was most interesting for them was the education in statistics and probability, which is sort of surprising to me because that's a master level course, and our students have a mandatory probability and statistics course in the bachelor. So I was like, oh, what's the problem? Then I talked to students, I tried to think about what happens, and perhaps there's a good reason for that, is that in a performance evaluation course, we are analysts. So we analyze things, and in order to analyze things, we have to really understand what we do. And what I discovered by talking in particular to advanced graduate students, that in data science, unfortunately, that's not the case. People, they don't focus on really understanding what happens and what they do with their big machinery. They're just busy making it work. And so in some sense, that might be why a performance evaluation course might be very useful, even though it's not the primary intended goal, but might still be useful. I'll illustrate this on three subtopics. And the first one is very methodological and very basic. So perhaps if we want to be utilitarian, we don't care about such things, but still, good students are worried when they do probabilities. When we teach probability in bachelor, depending on how we teach, I mean, if it's the math way, we'll talk of a probability space with the omega FP, blah, blah. If we do it more the engineering way, we'll talk of a sample space, and we will perhaps give a few axioms. And at this level, things seem perfectly correct and okay and well accepted. But then we ask students to solve problems that involve probability. And the feedback I received from students is that most of them are frightened by those. They consider it a terribly difficult topic where they don't really understand what happens. And I'm not speaking of physicists, that would be another topic of its own. The way physicists use probabilities is even more frightening. And many students simply don't understand what happens. And I think there is a gap between the basic probability we teach when we talk of throwing a dice and understanding what's the probability if you do it 3 times in a row that the sum of the numbers is odd, things like so. Elementary probabilities that are very easy and too simple, in fact, and their use in context of data science or graph theory. That's a true example that was mentioned to me by one student of EPFL. In a network data science course, one question they have at one point was consider a random graph and compute the distribution of degree. So probability pk that the vertex in the graph is degree k. Okay. And of course, if a good student or one of us looking at that would ask a number of questions. What is the sample space? What does the probability really mean? How do I compute it? But the student, in fact, usually skips the first 2 questions and is only concerned with the last one. How do I compute the probability? And so they go to the textbook because it's a hard problem. Many students don't find the solution by themselves. And if you take the very famous textbook that's used by many network data science courses, here is what you read. You read that the answer is given by the binomial distribution that is here, and the justification is given by 3 points. The probability that k of a link of a node are present is this. The probability that the other ones are not present is that. And then there are so many ways of combining this. You multiply those 3 numbers, and bingo, here is the answer. Okay. And well, if I look at this, then I'm completely puzzled, and I'm surprised that students accept this. But in some sense, in some of our courses, we're training students not to really understand what happens. So the university in itself, I think, is failing partly. So if I'm contrasting with what we do in performance evaluation, I mean, Gianfranco, you mentioned that simulation is not easy, and it's true because we do it in detail. And when we do a simulation, we have to really understand everything we're happening. And a stochastic simulation, we can view it as a specific implementation of a model where we assume that we have a random number generator that really produces randomness. And out of that, we have a random output. And when we do a simulator, everything is specified. We know what is random and why it is random because we built it. So in some sense, when I make a probabilistic statement about the output of a simulator, this is completely specified, at least if I wrote it myself, not if I'm using something from a package that I don't understand where it comes from. And in contrast to what the feedback I received from students about their difficulty at the network data science, at really understanding what happens and the perception that is extremely difficult, and after all, understanding some statements like this is not for us, so they just accept the formulas. In contrast to that, when they do a simulator in a performance evaluation course, it is perceived as the easiest and most enjoyable part of the course, by many of them at least. So why is there such a disconnect? Well, because perhaps we should view things as simulators, and the way we teach probabilities, I'm sure some of us do that, perhaps more you do it. I have a colleague in France, Bernard Icard, who does it also. When he teaches basic probability, he always couples that with discrete events, with simulators in general. So here is, for example, one solution to this small assignment of finding the degree distribution in a random graph. Well, we could do it the performance evaluation way. We generate a graph randomly, which would, by the way, force us to specify how we generate it. So we would have a number of parameters. Then for every output, we will have, for every run of the simulator, we'll have a random output. We can count the degree of a vertex, and we can do it 1 zillion times, and using confidence intervals for what is in fact Monte Carlo simulation, we could have a distribution in this way. But this is not the point I'm making, although that's a very important way. I mean, the very important things that some students realize when they do performance evaluation course is that there are many complicated things that we can first solve by simulation, a bit like was explained today with Kathy, I believe, who described this newspapers optimization problem. That's exactly a first point. But we can go, my point today is we can go well beyond this, is that we can view a simulator as a thought experiment. We don't need to program it, we just to imagine how I would do a simulator. If that's one of the things I repeat to students, particularly students who are doing systems. Sometimes they make statements about probability, and then I ask them, as a thought experiment, how would you design a simulator that would solve your problem by Monte Carlo simulation? Sometimes they're not able to do that, which means they have not even specified completely their probabilistic problem. Let's see exactly how such an approach would apply to our small graph problem. So one possible interpretation that a student in performance evaluation could do is, well, I take as parameters number of vertices of my graphs, the probability of an edge, and then I draw an edge with this probability, IID, and then at the end of that, I obtain one random graph. If I have a random graph, how do I get the distribution? Well, here I have, again, this ambiguity in probability. Is probability an empirical measure, or is probability a theoretical distribution that we put on unknown things? Here, one interpretation that would fit with this approach would be to count the number of vertices that have degree k, divide by n, and that gives me pk for all. But if my graph is large, I will have such a probability distribution, which itself is random. And this is not the textbook's answer, so probably my student thinks this is not what was expected from me if I look at the solution. So an alternative interpretation is, well, no, I have one graph, and the thing that is random is the vertex that I draw at random. But immediately I see that if I try to compute the probability distribution, it depends on the graph, not just on the proportion Q of connected pairs. So that's not compatible with the textbook solution. So it must be something else, which is that we draw both the graph at random and one vertex at random. That's the only interpretation that is compatible with at least the form of the solution. Now, having been convinced that this is the interpretation, if I compare my interpretation to the answer to the formula, I realize that the answer comes from another simulator. How do I get this formula? Well, because I draw edges at random, and I compute the degree of a vertex, of a specified vertex here. So it's a slightly different simulator that I've done. I'm not drawing one graph at random and picking a vertex at random. I fix the vertex and I draw the edges at random. This is what the solution, the textbook solution, is doing. So now we see it's not the same simulator than the simulator that supports the question. So the next thing to do to be convinced with the solution, well, is to reconcile the two. We have, in fact, two simulators that produce different outputs. And the thing to show is that the distribution of the thing we compute, of the degree, is the same for these two simulators, which is a small exercise in probability and conditioning that can easily be done. But unless you do this, you don't convince really students of your formula here. So if I look at the textbook solution and the one that's taught, in fact, in our network data science course in my school, there's no discussion of this. So I don't think there are many students who really understand any of the proofs that are done in this textbook here. Worse, if we follow the reading of the textbooks, we find this text that says, in a given realization of a random network, some nodes have many links, others don't. These differences are captured by the degree distribution pk, which was the interpretation number 2 of my random thing. So in fact, this textbook and the teacher who uses it oscillates between two interpretations. In one interpretation, we think the graph is random and the node is random, and in the other one, the graph is random, but the node is not here. So no surprise that students find probabilities difficult. It is not the probabilities that is difficult. It is the way we teach some uses of probabilities in some courses. And my first observation is, if we would always ask the question, in order to justify your formula or in order to justify simply the specification of the question, can you imagine as a thought experiment a simulator that would answer the question? And as I shown in this simple example, this would, at least here, reveal inconsistencies and perhaps make things easier to understand for students. So that was my first observation that came from when we go to speak of probabilities. So another observation, which is perhaps more well known, is that probabilities, in fact, and statistics can also be better explained with simulator. Here's a textbook's example. This is a viral infection of computers, not of COVID. And one of the questions that students are asked is to find what's the mean doubling time. So the invariable solution that data science people will do, that's a simple exercise. They will do least square fitting, and they will compute the parameters of the least square fit that will give a certain number. What is, of course, a bit less obvious is in which scale you should do the least square fit. On the left, I do it in the natural scale. On the right, I do it on the log scale. I can say if there's exponential growth, it makes sense to do in the log scale, but this is an ad hoc argument. And the troubling thing is that if I do it in one or the other scale, I have radically different results. So the answer to this dilemma is well known by statisticians. It is to model the noise, model the random part. And again, from here also simulators as thought experiments can help. We can view, in fact, classical statistics in the language of performance evaluation by saying that the data that I have which is of course done by nature or by things of society, but we imagine when we apply classical statistics that in fact it's done by a simulator, the kind of simulators we do in class, that has an unknown parameter. So the code of the simulator has a number of parameters, and those parameters are not known to us. And the problem is, after seeing a number of outputs of the simulator, can you say something about the parameter? So that's, of course, is exactly the same as what people say in statistics, but for students, it is, as my feedback I have from students show, that's a very, very fruitful and useful way of thinking about it. For example, in this case here, specifying the simulator is equivalent to specifying those little formulas here that specify the form of the output. And since we have specified this, of course, the very easy thing to do is to estimate the residuals and looking whether the residuals are consistent with the simulator assumption. And we see that in natural scale, they are not at all. There is no way this could be an ID sequence, Gaussian ID sequence. On the right, there is some chance that it is here. So forcing to specify the model gives us, in this case, a very easy discrimination of which model makes sense. Third point that I would like to illustrate is also when we do performance evaluation, depending on the focus of the course, we may give more or less focus to queuing theory models or also to what is called operational laws. Operational laws are also like Little's law, utilization law, force flows, interactive user model, etc. All those laws are in fact very easy to express in simulation. And I'll give an example here where it's easy also to have your own law, because in reality, when we try to apply those operational laws to practical systems, very often they don't match exactly. But if we work for just half an hour more on the system, very often we can find that, oh, there's an easy way to devise an ad hoc law for this one. Here's an example that is very often discussed here in Switzerland about the accuracy of the train system. So the train system companies always have 95% or more accuracy, but the people who commute between Lausanne and Geneva, they say, well, the probability of being late is much larger. So in this hypothetical example, I'm assuming a consumer association has done a survey of its participants, and they find a rate of late arrival much larger than the train company. What is happening here? Is are the data wrong or not? No, this is just a sampling problem, and sampling, change of sampling is what is called, at least in queuing theory, pound calculus. But it is present in many instances. For example, here's a recent paper, not so recent, a SIGCOMM paper of Jennifer Rexford and co-authors about the distribution of file size when you sample per packet or per flow. And you see that you have different file sizes. And here, a pound calculus formula would simply relate the two. That's an example that is well known and found in textbooks. Another one that is well known is Little's formula, but is what is perhaps well known but not so much well known, is that Little's formula can be derived in a simulation. So I'm back to my topic of the day, simulation. Little formula is here, the average number in a system is equal to the rate in or rate out, if the system is stationary, multiplied by the average response time. And how do I prove this? Well, if I do a simulation and I estimate all of those quantities by different counters and I mix and match all those things, I found that if I have reasonable assumptions, the reasonable assumptions are about what happens at the two ends of the simulation when you have customers that have come in and not yet come out. So here you will have a certain approximation to do. But if you ignore those little epsilons at the ends of the simulation, you will find that this relation is simply an identity between the different things you measure. So in some sense, Little's formula, that if you show it in the classical theory, queuing theory context with pound calculus, is a bit impressive and needs the probabilistic techniques. But in reality, it comes from just how you combine things that you count and the way you draw your statistics in a simulation. We can do the same for exactly the point that I was making before, those two estimates, the two sampling methods. I can reconcile the two estimates by analyzing in detail. If I simulate a train system, now we're not talking of computer system, but we have also many students who come from transportation classes. If we simulate the way we measure those different things, we will find also a relation of this kind here that says that the two estimates are related by the ratio of the proportion of passengers that are in late trains. And if the number of passengers in late trains is 6 times more than in average train, then both estimates are completely compatible here. So this is an example where reasoning in terms of simulation, the way we do it in the theory part of queuing of a performance evaluation system, the course can really help a lot. So conclusions, Gianfranco, carry on, continue to teach simulation because it's vital. teaching simulation is important, because once students are used to teaching simulation of stochastic systems, well, having done that, they're able to do it as a thought experiment. And I've shown 3 topics where it can bring a lot. First, remove them, give sense to probability, because many textbooks, not many, but some textbooks and some statements I read from various classes on probability, I have a hard time making sense. And it would be easy to solve that problem by forcing, as a thought experiment, to imagine how you would simulate something that would allow you to compute this with Monte Carlo simulation. Of course, classical estimation theory and classical statistics are easily explained also in the language of simulators, and difference in sampling viewpoints also can easily be quantified, and identities can be found by imagining how you would compute them in a simulator. Voila, that's, thank you
very much.
And those are the references that I mentioned in this course. That I guess the slides we will be able to make, or I'm not sure, will we post the slides of this talk?
Yes, I think we post all slides.
Well, thank you for your attention.
Thank you, Janives. Question for Janives?
Like the talk. I always like the inspection paradox, so that's great.
Thank you.
Andrea? You raised
I love this example of the number of passengers being sampled giving a different result from the number of trains being sampled. That also helps you to make a decision that if you're going to delay trains for engineering works or something, you want to do it at a time of day when you have fewer passengers, because then you'll make fewer people unhappy. So the way you're doing the sampling also affects the kind of decision that you're going to make.
Yes. And if I may add, I mean, this is the value of analysis. Perhaps there was a lot of discussion before, or is it really attractive performance evaluation course, because students are more computer science students out here in my university, is true, are much more interested in building things than analyzing it. That is true.
Yeah.
But it is true also that taking the analyst hat once in a while gives you forces you to think about the system you're designing in different ways. So I think it's quite useful to spend perhaps 10% of the time that you design a system analyzing it as well.
So a quick comment. In fact, every year when we present the student project, often the best project is end up using integrating simulation together with experimental design to find the best solution. Mm-hmm. So I think that's a very interesting view. Like, how should you kind of incorporate the experimental design, in finding the optimal performance?
Yeah, I took simulation from Alan Pritzker, who was one of the pioneers of discrete event stuff. He made his students write very detailed reports in a managerial style about what they were seeing in their simulation exercises. So there was a lot of emphasis on what kind of design choice was going to be made based on the output of the simulation. He was an industrial engineer, by the way.
There is a question on the chat from Tai, or is that like operational analysis? The third part, yes. The third part is operational analysis, is essentially what I was presenting. Yes, it's the same.
We need to get people to look at the transients too, especially when we have the kind of variability that Moore was talking about, or the kind of saturation that we saw in Kathy's examples this morning.
True.
So we are almost in time. Mm-hmm. If you do not have other questions, we can have our break if you want. And so
I guess there's kind of a question here related to what we were discussing before. So I think that we all in this group really see the value of analysis. So we have no problem, like we would be happy to take your course and, and go through the analysis and learn all this analysis. But it's not always obvious to how to convince students of the value of being able to think rather than just build, design the system rather than just dive in and start building something. That's the discussion we were having before. I mean, my only solution to it was start them younger. Like, so I started in an undergraduate class. They have to learn all this stuff in an undergraduate class. Maybe the answer is even to start it in high school.
I think if we have to, maybe if we can persuade them by saying that if they want to go up the managerial tree, they have to learn how to do analysis. They have to learn how to persuade managers.
Yeah, I don't really have an answer. I don't know.
I don't either.
Just an observation. Can you hear me now? No. Yes.
Yes.
Just an observation. I agree with Yves that the difference between probability theory and probability in practice is really a big gap. And when we are teaching our performance evaluation courses, we are really, in some sense, bridging that gap. And in fact, many students then they are realizing that they start to understand really understand some of the things that they learn in the basic probability course. I don't know if that is due to the fact that I think it is really due to the subject per se. It's not really a merit of the teacher or not. I'm probably not a good teacher, and so I don't take any merit for that. There is another thing, is that the way in which we were mentioning the relation between simulation and things in practice, then the problem is that our courses, at least my experience, so I hope that is not your experience, is that the number of hours is being reduced and squeezing into a small number of hours. Not only what I really think that is important, the explanation of the basics, really the discussion of the basics, but also the type of experimental thing that you can do with simulator, because I agree completely with Yves. For instance, for the Littlest formula, you can even do more, because you can also take into account the boundary part, which is really where the formula is not working perfectly, but you can see what kind of correction you should introduce if you really want to make sense. And you will see that, of course, if the simulation is long, those corrections are just negligible, and so they go, so everything works fine. So, but having time to really get in at this level of detail and to get to this level of discussion really takes time. I started to teach courses here in Torino in 1978 in simulation, and my course was about 100-hour course. Now I have 48, 45 in Iowa State. And of course, I have to really remove a lot of stuff. A lot of things that I was doing at the beginning is not done anymore. There is really, and I still find problems in really squeezing into these hours all the things that I think that are really relevant, even if my course is a very basic one. Really, I'm not getting to at any level of, it's not really detailed one at all. I think it's also very easy, but students find it very difficult because they do not have really time to see too many applications. And that is also why I was saying before that probably I would need to work with something younger so that we can help each other in discussing the more theoretical stuff in the nice manner, but also really complementing those things with more practical, more attracting also visualization of things. I am really not doing any kind of visualization. I am asking every week, Every week, the students have to implement, they start to implement a very basic simulator, and then they add every week an additional blocks to the simulator until they get at the end of the 8th week, they have the bricks to address a final project, which is a little bit more complex. But time is really squeezing into a small amount of time. All these things is really difficult. I found it very difficult.